Hello, everyone. Welcome to this week's edition of zkStudyClub. Today, we're proud to host Zac Williamson of Aztec Protocol, and he's going to be talking to us about his recent work on Goblin PLonK. So thank you very much for being here, Zac. Over to you.
Cheers. Thanks, Alex. Hey, everyone. So yeah, Goblin PLonK. What the hell is Goblin PLonK? So this is some work that I've done, like we've been doing recently about how to do efficient recursive proof composition. It's also, there's been a lot of research that's come out lately about folding schemas using sum checks. So this is adjacent to that, but I think it can be combined in very interesting ways, which perhaps we can discuss at the end. But yeah, so that's so hang on. How do I advance slides? There we go. So what's the problem? So Goblin PLonK is not a general purpose scheme for recursion. It makes a few assumptions that may or may not hold true for certain applications in the zk trade-off space. So the idea is that you have a setup where you have a very resource-constrained prover that's constructing zero-knowledge proofs, where what one wants to preserve privacy, and this prover also wants to perform arbitrary depth recursion. But the expectation, the assumption is that there is also in this network a very computationally well-resourced prover available, but they're not trusted, so they cannot. You don't want to give them any secrets, and also the actual amount of the communications bandwidth between the two provers is quite limited. For example, if you're say building a privacy preserving layer 2, and you have a resource constrained prover submitting proofs to a mempool, for example, that represent transactions to be aggregated, to be sequenced, then you have this model where basically client side, you've got a very wimpy prover, you want to be able to recurse, then once your transaction gets picked up by a sequencer, by prover, you have a very resourceful, you have access to a lot of compute, but you can't trust it, so no privacy, and the limited bandwidth between the two, for the same reasons why Ethereum transactions on a peer-to-peer network can't be too large. So I said we're insensitive to final proof size. So that's actually kind of contradicting what I just said. By insensitive, I mean it's tens of kilobytes, not megabytes. And the final verification costs don't matter because of this resourceful prover. So yeah, recursion. So just to summarize briefly the zk snark recursion problem. So if you're defining a snark over elliptic curves, then your circuit will be defined over some curve where the arithmetic of your gates is going to be modulo the number of points in the curve, which will be a prime subgroups. And so to verify a proof within a proof with one elliptic curve, you need to perform arithmetic in the field that the curve is defined over, and that's going to be different to the curve that the native modulus that your circuit arithmetic is performed over. P does not equal Q. This is the problem, and it's not good. So there are several solutions. I'm just going to run through briefly from historically. The obvious one is brute force it. You use your native prime field arithmetic to emulate a binary arithmetic, and then you use your emulated binary arithmetic to emulate the prime field arithmetic that you really want to do. But layer on these two abstractions adds a lot of costs. So it's like about 300,000 constraints to verify a simple proof within a proof under this model. So it works, but it's very expensive. It's it's like it's not good at all. So the next solution, and this is the current one that everyone's using over elliptic curves, the one that's really very elegant is using Halo 2 curve cycles. So you have two curves A and B where they form a cycle because basically the fields are swapped. So the coordinate field of one curve is the same as the native field modulus of the other curve, and vice versa. So you can't create these cycles where both of these curves are pairing friendly, but that doesn't matter because of accumulation schemes that Halo pioneered. And it means you can defer all the expensive non-native elliptic curve operations you need to do to verify a proof within a proof. You can kind of defer them by kicking them into a circuit defined over your cycle curve, where they become native operations, which is very efficient. So this is kind of the best way of doing it so far, but it does have some drawbacks. In practice, your protocol logic is probably if you're encoding some kind of protocol, you want that to be over one curve, so you only have to deal with one prime field modulus. so you're going to use your cycle curve strictly for recursion, i.e. you're going to embed like a snark verify algorithm within your cycle curve, and that's the only circuit you're proving of your cycle curve, which kind of means that to recurse once over your main curve, you really need to verify 2 proofs, one over your main curve, one over your cycle curve. It's kind of expensive. That's lots of hashing to do. And also, at each layer, you still have a relatively chunky amount of non-native field arithmetic to perform. You can delegate the group operations to that curve. When it comes to actually verifying the proof over your cycle curve, you have this intersection where you're going to have a snark proof over your cycle curve, and some public inputs of that snark proof will relate to claims you want to make in your main circuit. And so the claim is going to be defined over your native field modulus. The public inputs will be defined over your cycle curve's native modulus. There's a non-native field matched up there that you really can't avoid. I'm not aware of any ways of avoiding it. So it's better than the brute force method, a lot better, but it's still got some drawbacks, curve cycles. And so this then leads on to Goblin PLonK, which is very much an iteration. I see it as an iteration on Halo 2, which is the idea is, can we basically avoid doing this expensive curve bouncing step? And so some of the one of the key concept Goblin PLonK uses is this idea of an instruction machine. I think they're called state machines in other places. I very much pinched this idea from Geordie when I was chatting with him about zkVM. So this is very much coming from him. But the idea is that if you have some complex operation you want to do inside a circuit, instead of performing instead of like evaluating the arithmetic in your circuit, you cheat basically, and you write the instruction you want to perform into a lookup table along with the claimed output, and then you carry on with your life inside your main circuit. And the idea with an instruction machine is you define an instruction set of like nasty functions, basically. And whenever you're in your circuit, you come across you need to evaluate one of these nasty functions. You just write an instruction inside your instruction machine going, here's the inputs to the nasty function, here's the claimed output, I'm going to move on with my life. And the idea there is that the benefit of that is that you can take that lookup table and convert it into a transcript, multiple transcripts, where you have basically a commitments to the set of, like, you have commitments to all of the claims for specific instructions, and then you can construct bespoke snark circuits solely to prove the correctness of one instruction over and over and over again. This is very nice and efficient because you can create like a custom very wide circuit for each of these instructions, where you can define like the optimal algebraic constraints specifically for an instruction, for example, like Ketchak or non-native field arithmetic. And generally, wide circuits are going to be much more prover efficient than narrow circuits because you're doing less wire copying, and also every degree of your polynomials, like every constraint in a snark circuit has a constant cost associated with computing the opening proof, which goes away.
I think Dara put in the chat, he just linked, I'm commenting here for folks who are watching the video. So there's a link to a GitHub issue in Halo 2, in the Halo 2 repo, which I will put on the YouTube link. But I don't know, Dara, do you want to mention, you just want to give some context around that comment? If you can't talk, that's okay. Bottom line is, what he said is the best way we had to avoid native arithmetic for public inputs for Halo 2 is in this issue. So yeah, so anyway, so folks, I'll link this in the video. I'm sorry to interrupt.
Well, yeah, I'm not up to date with the latest and greatest in Halo 2. I'm aware that the noise is a problem. I'm not familiar with the latest on how to avoid it. So yeah, cool. So we have this idea of an instruction machine that was fermenting in our heads around. Basically, if you want to do complicated operations in your snark circuit, you cheat, you put them in a lookup table, then you make it somebody else's problem. And then the idea is you can construct proofs of these instruction machines to prove all of the correctness of the transcripts. And so what we're thinking with this is, well, hang on a minute, we have a nasty function we need to do. And I'm stealing Ariel's nomenclature here. He was talking to me about proofs of nasty functions. So we have this nasty function we want to do, which is non-native elliptic curve arithmetic. It's particularly scalar multiplications. So why don't we just shove those in a lookup table and forget about them, and try and find a way of like solving this problem at some abstraction layer which is not like within a recursive cycle of circuits. So one of the things we do here, well, another concept we need is this concept of transcript aggregation. So the idea is inside your snark circuit, you want to do elliptic curve scalar multiplications. You don't, you cheat. Instead, you write them into a lookup table. So you can use something like lookup, or there's like one of the stuff that Oracle has been doing, or whatever. Like there's loads of techniques, but the basic core idea here is that what you're doing is at the end, like the result of this operation is that you have columns in your circuit which describe the elliptic curve scalar multiplication operations that need to be performed in their claimed outputs, and that those columns are going to become basically directly translate to polynomial commitments. So you have basically commitments to your transcripts at each recursion layer. And so the idea is you need some way of doing transcript aggregation, basically combining, aggregating multiple transcripts, so that at each layer of recursion you're just tracking one transcript. And so this is not a folding scheme, because in Goblin PLonK, the size of the transcript grows as you recurse. If you have, imagine you have two snark circuits that both need to perform non-native scalar multiplications. The result of doing the aggregation is just you have a transcript polynomial, which is just the sum of the input transcripts. So this isn't too much of a problem, because if one entry inside this lookup table is going to be an instruction to do like a non-native scalar multiplication. So there's not going to be very many of those per circuit. So this transcript is not going to grow particularly quickly. So the degree of the transcript polynomials is going to be relatively small compared to the degree of the circuit size. And yeah, if you're using multilinear, if you're using some checks and multilinear color commitments, there's just some really, really nice ways of like trivially aggregating transcripts. I can get into in a bit. And so the final technique with Goblin PLonK is this concept of curve transposition, which is very much stolen from EIP 4844, where the idea is you can prove the equivalence of commitments to the same set of data over two different elliptic curves. And so this is very useful, because effectively what I'm trying to get to here, what I'm trying to build up is that in Goblin PLonK, what you end up with is you're recursing repeatedly over and over again at in some recursion stack, and at each layer of recursion, you're running a brute force verification algorithm. However, whenever that algorithm comes to the point where it needs to do elliptic curve scalar multiplications, it doesn't do the multiplication, it shoves your instruction into a transcript. And then you combine those transcripts as you recurse. And so at the very end of your recursion stack, you're going to have this chunky polynomial commitment to your transcript that you then need to prove the correctness of. And so how do you do this? Well, the trick here is that you commit to the same transcript over your cycle curve. You prove the equivalence of the two committed polynomials, like the data within them, and then you construct a proof of correctness for your elliptic curve scalar multiplications in a circuit defined over your cycle curve, where all of the operations are now native scalar multiplications, not non-native. And so, it reduces the complexity by about 2 orders of magnitude. And so how do you do curve transposition, right? I've just glossed over this. Well, okay, you have two commitments over different curves, over different prime fields to the same information. Well, there's no magic bullet way of doing this, but there is a way that's pretty fast. What you do is you just use a regular polynomial commitment scheme like IPA to open the commitment over your cycle curve at some random point. And then you construct a snark proof of your main curve, where the polynomial commitments form columns in your circuit. And the circuit is basically a bespoke circuit tailored to do non-native prime field operations, where you, as a public input, you take in the random challenge you used over your cycle curve to open those polynomials, and you literally kind of, in your circuit, you iterate over the coefficients of your polynomial, and you construct the evaluation of that polynomial in the field of your cycle curve. So you're using non-native arithmetic, which is not particularly difficult to do. It requires, for each polynomial, each degree of your polynomial, which in this case is going to be an instruction to do an elliptic curve scalar mul, requires one non-native field multiplication, one non-native field addition, and you can just combine that. You can just create one big chunky constraint that does that as a primitive operation. So that's a lot of information, big info dump. But this is to try and summarize it all. You want to do your main recursion of a curve A. And so the scalar multiplication operations of a curve A you need to do when you're verifying, you delegate that to this imagined elliptic curve virtual machine via this instruction machine process where you're shoving the operations into a transcript. And then at each recursion layer, you're aggregating the instruction machine transcript produced at the current layer of recursion with the previous aggregated transcript. And then at the very end of the recursion stack, you provide a proof of correctness for a transcript to the elliptic curve virtual machine. And this is going to be defined over your cycle curve. And then you use curve transposition techniques to validate that the transcript you shoved into your elliptic curve VM proof is equivalent to the transcript that was built up in your recursion stack. So there's some funky sequencing you've got to do here to make sure that your challenges are generated in the right way, so that you can't do rewinding attacks. But this is the overall architecture. It's not particularly simple or elegant, but I do believe it is very, very efficient. So to try and dive into this in a bit more detail, so you're at each level of recursion. So this red square is basically defined is the idea is that you're constructing a proof of a snark circuit, and the blue squares is basically an aggregation algorithm. So you're saying, okay, as you're constructing proofs of proofs, you want to verify, run a recursive verifier on the previous proof. Technically, it's not a verifier, it's an aggregator because it's not fully verifying the proof. And each layer, you're shoving your expensive operations into these transcript commitments, which are part of the proof. And then once you've finished with your recursion, you have this final proof. And within that proof, you're going to have commitments to your transcript polynomials. And so you run this instruction machine circuit, which basically takes as an input the transcript polynomials, I'm doing things out of order. Like at the very end of your recursion stack, the next thing you do is you make this ECC VM proof. So the idea is the prover knows, okay, they know what's in the transcript. They commit to the same information over your cycle curve. So obviously, like you need to make sure that there's going to be some range checks involved here to make sure that you're not overflowing the modulus with both contexts, where you prove the correctness of a bunch of elliptic curve scalar moles over the cycle curve. So it's all nice, it's all native, it's all cheap. And then as part of making that proof, the prover will have to open those the transcript polynomials committed over the cycle curve at a random point. So we're going to reuse that. And we're going to then feed that information into the instruction machine along with the original transcript. And what the instruction machine is going to do is it's going to produce instructions for a non-native field virtual machine to where the instructions are going to be what's the non-native field operations that need to be performed to evaluate the coefficients of the transcript as if they were coefficients committed over the cycle curve. And then those instructions get fed into a non-native field virtual machine. You get a proof out, and then boom. At the very end of this, you have 4 proofs to prove instead of 1. But the idea is that you now, basically it's a way of minimizing the amount of work that this prover is doing, because the idea is that you have these 4 proofs, they're succinct. You can kick them off to some third-party aggregation service to combine, and you don't particularly care about the costs of verifying these 4 proofs as long as they're succinct, so it's not too painful. Succinct-ish. Anyway, should I stop on this for questions? Because I know I've just gone through a lot of info here.
Yeah, thanks. This is great. Does anyone have questions? So Dara is putting in some comments.
Let me
Dara, if you want, we cannot hear you, Dara. So if you've been trying to talk, then yeah, there might be an issue with your mic. We cannot hear you. If you want to type your question, okay. So Dara's going to rejoin and come back. Does anyone else, while Dara's doing that, does anyone else have questions for Zac? Maybe not. Okay. Yeah. Everyone maybe still processing the slide. There's a lot of information on here.
Yeah.
But
well, like if folks
also, quick question. So basically, what is labeled as like pi, the honk proof, does that include the transcript from all the instruction machine calls? Okay.
So it includes the latest transcript. So the idea is that I'm going to get into this in a future slide, but the idea is each proof contains basically the old transcript and the new transcript. And you can very easily, if you're using multilinear stuff, you can very easily derive the current transcript from the old transcript and the new transcript. And in doing so, you implicitly are also proving the correctness of the aggregation, that the old transcript plus the current transcript equals the new transcript. So this alpha proof doesn't contain all of the transcripts of the previous proofs. It contains two transcripts, like the transcript of the previous layer and the transcript of the current layer. And the transcript of the current layer contains the aggregation of all of the sum of all the instructions that have been added as the proof has been recursing. Daira, how's your mic? No, we can't hear you. Sorry.
Nope. If you're talking, Daira, we can't hear you. Srinath just asked a question: do transcripts grow in size as more steps are executed? I believe you said yes.
Yes.
But, yeah.
So I'm making a very explicit, implicit assumption here, which is that every entry into a transcript describes a expensive operation to perform, and therefore the transcript will grow at each recursion layer. But the idea here is that the overall size of the transcript is going to be much smaller than the degrees of the polynomials that you're committing to for your circuit, because like to give an example, like to do a non-native scalar multiplications between like 4 and 20,000 constraints, and that becomes one degree of your transcript polynomial. So it's it does grow, but as long as each instruction represents something expensive, the assumption is that's not going to be a problem.
Can you hear me now?
Yeah.
Yes.
Excellent. Okay. So these 4 proofs that you get out at the end, what kind of proof are they? How big are they? How expensive are they to verify?
So the assumption. Okay. So I'm making some explicit. I've described some explicit curves here. So the way we're planning on building this is using a half pairing friendly cycle, where the red proofs would be fairly succinct, and one would have seemed very cheap to verify. Like these virtual machine circuits, the assumption is that they'll be quite wide for maximal prover efficiency, so like 70-ish columns. So not trivial to compute to verify, but like you're talking like 120 or something scalar moles possibly for each proof. And then the cycle curve proof will be more expensive because the assumption is the commitment scheme will be IPA, and therefore there'll be this linear time step you need to do where it'll be linear in the degree of the VM circuit. But so the efficiency of the elliptic curve VM circuit matters a great deal. The current kind of like architecture we have, at least on paper, we haven't built it yet, can do one like variable base native scalar multiplication in 8 rows and about 70 columns. So the assumption is that the degree of this elliptic curve proof won't be that large and can be stomached by whatever verifier is going to be consuming this proof.
So the red proofs here, if you're using the half pairing cycle thing, the red proofs are KZG proofs on the ECC VM is an IPA proof. Why that way around?
So it doesn't have to be that way around. The reason we would do it that way around is because KZG is much cheaper for the prover to compute an opening proof for than IPA. So it's just going to be, if one is ruthlessly focusing on optimizing the proof efficiency for the person constructing this Goblin stuff, you'll want your main recursive circuit, your main circuits to be over your cheaper curve, which will be the KZG curve. But yeah, there's no fundamental reason you could flip the curves around.
I see. Or you could do one step of a halo recursion to move that the pink proof to be a KZG proof.
Yeah. Or you could just, you don't need a half pairing friendly cycle. I'm assuming this abstraction will also work for if you're using Pastor and Vela curves. because I saw your comment where you're saying it's similar to what you folks are doing with Halo 2, but like deferring the other curve root. Yeah, exactly. I mean, I was looking at Halo 2 and thinking like, how can I avoid verifying this cycle curve proof at every layer? I don't, because it's because I was way too lazy for that.
Yeah, unfortunately, it's too complicated for me to explain. If you look at that ticket, then there's a diagram which shows it's a data flow diagram showing where everything goes. But to try and explain it in a video, I don't know how I would do that. Sorry.
Fair enough. Yeah, I can't look at the ticket because I'm sharing the screen, but I will look at it afterwards and pick your brain on it. But there's also an additional considerations because we're building this like honk proving system, which is very much like HyperPLonK, where it's using sum checks, which is like really, really nice for the prover, very, very efficient, very fast, no FFTs. But one of the downsides is that the verifier is got a logarithmic number of hashes to do. So actually verifying proofs is not like the grunt work that the verifier is doing outside of the non-native arithmetic. It's not completely trivial anymore. And so, yeah, so the idea of having to do like verifier, like at each layer of recursion, like verifying another proof over the cycle curve, plus the non-native field arithmetic was like, not good. So we were thinking about, yeah, like, so let's just not bother, let's be lazy.
But just to put it back in the context, you're assuming the verifier here is like a roll-up server, right? That theoretically has, some stronger abilities for,
exactly. If you send all these 4 proofs to a smart contract, then that smart contract is going to cry, and it'll cost you hundreds of dollars in gas fees because of the IPA verifier. So there is that assumption.
Cool.
So I guess you can have some kind of hybrid where periodically you compress your application proofs, but you're not doing it on every step as you would in the original Halo paper.
Yeah, exactly. Because this is not this construction is not really succinct because the transcript grows as you recurse. So yeah, as you said, like you can just fix the recursion depth to some hard limit, and basically then like wrap a box, like fix the recursion to a hard limit, and take that entire protocol and just put it in a box and say that this is now your recursion primitive, where the idea is like instead of doing like Halo 2 recursion at each recursive cycle, you do Goblin recursion for like 100 cycles, and then you take all these 4 proofs and then you recurse those using Halo 2, and then you have a generic accumulation scheme that doesn't have any like linear growing term.
Yeah, it's eventually we're going to work out what the most efficient way to do this is, but everything's all up in the air at the moment.
Yeah, and another useful application of this is folding schemes. So foldings have become quite popular recently, and there's been lots of really cool stuff done with them, with like Sangria, Nova, Supernova, Hypernova, and
sorry, since I'm sorry, just because he's here, Srinath, author of I think hello Srinath. Hopefully you can make maybe you have some comments at some point about comparing and contrasting or commenting on the applicability of those schemes there. But anyway, I didn't mean to interrupt you. I just wanted to call it that Srinath is here, and he presented I think 2 weeks ago Supernova.
Yeah, so I mean, like the thing I'm thinking about here is that if you're using something like Hypernova, where you need to do one. I believe like if you wanted to use Hypernova for IVC, you need one non-native scalar multiplication for each fold, which isn't very much work, but 0 work is better. So instead of actually doing that, you just use Goblin PLonK. So you just add each time you have each fold, you just shove that non-native operation into a lookup table, and then after say 100 or so folds, maybe you or like add some fixed constant number of folds, you then do this transition step to prove the correctness of the scalar moles, and then you go again, and it takes an already like relatively low cost of folding and basically makes it disappear, I think.
Yeah, I just noticed you got on the slide the sizes of all of these intermediate things in terms of group and field elements. That's interesting. They're smaller than I would have expected.
Well, like take them with a grain of salt because not implemented them in code yet. So could be making some optimistic
could have missed
estimations. Yeah. Well, maybe we should move on then. So in terms of costs, so the napkin math here, as I'm thinking, each non-native scalar multiplication instruction reduces to doing one native scalar mul in the ECC VM and 5 non-native field operations in the non-native field VM. And why 5? It's because one scalar mul instruction in the VM needs 5 columns. You have 4 for your X and Y coordinates because you need to split them up into 1 to 8-bit chunks. And then you have 1 column for your scalar multiplier. So that's 5. But if you depends how you slice it. I mean, you could if instead of the VM instruction being do a non-native scalar mul, the VM instruction is batch do 15 moles required to verify proof or whatever, then that would get reduced. But these are like the rough napkin math for Plonkish constraints. I reckon that like the Goblin PLonK costs are probably about like 8,000 Plonkish. Like by Plonkish, I'm imagining like width 4 ultra Plonk, because that's the one thing I'm most familiar with. So my claim, which I'm not yet proven in code, is that the costs of like doing one layer of like PLonK or ultra Plonk recursion reduces to about 8,000-ish Plonkish constraints plus the cost of the rest of the verifier algorithm. I think we can do better than that. My hope is all in the cost of one layer of recursion, getting it down to about 8192 Plonkish constraints. That's my goal at least. But until I've actually shown that
sounds feasible.
Yeah. And like that with this, that basically makes recursion just like a disposable primitive. You can just throw in everything because it's so cheap, which would be pretty cool. So yeah, I don't know how we're doing for time because I have a few slides for like the details for the VM designs, etc. But they're somewhat tangential.
Yeah, we're good.
Actual...
I mean, well, just so you know, it's we typically go up to 90 minutes, so there's still an hour left in the session. So I think I think we can proceed. We got plenty of time.
Yeah, I'm fascinated.
All right, so this instruction machine stuff. So technically, for what I've described the Goblin PLonK, you don't really need this concept of an instruction machine because you only have one instruction, which is do an elliptic curve scalar multiplication. The reason why this instruction machine abstraction I think is useful is because if you're doing Goblin PLonK, you might as well build an instruction machine into your protocol architecture and use it for more than just elliptic curve operations. For example, you could have an instruction machine to do Kerchak rounds, SHA-256 rounds, big integer arithmetic, etc., etc. So I figured I might as well just describe a little bit how it works. So again, there are some kind of explicit details here which are not, you could generalize this a lot. So I'm saying the transcript has 4 columns. That's because we're planning on building it, adding it into a width 4 Plonkish proving system. So if you had more columns, you probably want your transcript to be wider as well. So the idea is the width of the transcript is going to be the same as the width of the circuit that you're making a proof server. Where what did I say? M describes the transcript size. Okay, so one convention we could do is how do you actually get instructions into the transcript? Well, like the simplest thing you can do is you just have a convention where the transcripts, like the instructions that like the constraints where you're writing into your transcripts, you put those at the very start of your circuit, and then you just have a selective polynomial which copies them across. And then if you need the transcripts outputs elsewhere in your circuit, you copy constraints. So that's just the simplest way of doing it. You don't even need permutations or lookups. And so this is the idea of an opcode. So again, I'm like assuming that you have some elliptic curve endomorphism to break up your a 256-bit scalar mul into 128-bit chunks. And that's what lambda here is. So the idea is the instruction will be you have these 2 128-bit scalars, z1 plus lambda z2 times p, add it into an accumulator array. That will be the opcode. So here, this is like a weird work example that I'm struggling to understand. So the idea is that just as an example of what one could do is like the first column here is the opcode value and then the second and third columns are like define your x coordinate. The fourth and the like y4 and y2 describe your y coordinates, and y3 and y4 describes z1 and z2. And so the idea here is that this elliptic curve instruction would exist in your transcript over 2 rows. So I think what I was trying to get at here is that you can, if you have a very complex instruction for your instruction machine that requires more entries than you have room for in your transcript, you can just split it. You can just pack that instruction across multiple rows. And so here's just a little bit of an aside for if you're using a multilinear proving system, how do you aggregate transcripts? Because it's really nice and simple. So if you're using a multilinear proving system like PLonK or PLonK, which is still not yet published, but we'll see. The idea is that your sum check requires multilinear polynomials, but multilinear polynomial commitment schemes are not the best. They're very painful. But there's a very nice technique that was applied in the Gemini paper where you actually commit. You have a transformation layer where you have a protocol which transforms claims about the evaluations of multilinear polynomials to claims about evaluations of univariate polynomials, and you actually commit to your polynomials. So in univariate form via univariate polynomial commitment scheme, where typically the representation is just that the coefficients of a univariate polynomial are the kind of the vertices of the Boolean hypercube that you are multilinearizing. Just as an aside, this is a really nice way of doing things because hello, was somebody saying something?
I heard that too, okay. But there may have just been a mic misfire. So keep on rolling.
One of the nice things about these transformation layers is it means that getting shifts is very nice. So for Plonkish systems, you need it's very helpful to have a cheap way of getting commitments to your shifted input vectors, witness vectors. So if you have if you're representing your polynomials in univariate form, you can get the shift trivially by just multiplying your polynomials by x, which is easy to do. But basically, so the idea is you have some univariatization map, which maps univariate polynomials to multilinear polynomials, where your coefficients of your univariate polynomials represent the vertices of the Boolean hypercube. Why does this make it nice to aggregate transcripts? Because you literally just combine them. So the idea is that let's say at some layer of recursion, you have a commitment to the transcript of the previous layer, y old, and you have a commitment to the transcript at the new layer, at the like the y new. And the idea is that you can take the difference between these two to extract the transcript at the current layer, which is kind of pretty easy to do because you literally I'm assuming you've got an additively homomorphic commitment scheme here. You just subtract the old transcript from the new transcript, and that gives you the coefficients that you want. It's just that they're at the wrong monomial powers. So you just downshift by 1 over x to the m, where m is the number of entries added at the current transcript layer. So I'm making some assumptions. I'm making an assumption that the number of entries added into the transcript is part of the verification key, so it doesn't vary for a given circuit. And then you can just do some simple consistency checks. So you basically say, okay, you derive this transcript polynomial yx by taking like the difference between the new and the old transcripts. And then just downshifting by x to the m. And then you do some consistency checks where you just check that this output polynomial, for all of the degrees that are higher than m, there's no data, that you have everything is 0. And similarly, you do this copy check again, basically where you're saying that for the first m rows of your circuit, where wi are the y commitments to your circuit. For the first m rows, your transcript polynomial and your y polynomials are equivalent because you're writing instructions into your transcript. So I can go into this in more detail, but this is kind of just a bit of implementation detail. It's making a lot of assumptions about the proving system that's being used, which is kind of independent of Goblin PLonK as a scheme. So this stuff is only useful for like multilinear sum checky systems. So yeah, So VMs. I mentioned before that we have the concept of like an elliptic curve virtual machine and an non-native field virtual machine. These are very primitive VMs. And the only reason they're VMs is because I'm making an assumption here that when you're recursing in Goblin PLonK, the circuits that you're recursing over are not uniform, as in they're different. And by extension, the verification algorithms will be different, which that means that by the time you've finished doing a bunch of recursions, you don't know, like the actual arithmetic that you need to perform in your transcript is not going to be known ahead of time. If it is, then you don't need a VM. But to give an example of why this may not be the case, like even imagine you're recursing, you're verifying multiple hyperplonk proofs or honk proofs, because the verifier algorithm, how do I put this? The verifier has to do with scalar multiplications. That's a logarithmic in the circuit size. So if the circuit size of each circuit in your recursion stack is different, then you're going to need to do different operations. Similarly, if you may have different arithmetizations at different layers, with different polynomial identities, with maybe more which means you may have more wire commitments, more advice wires, etc. So the assumption I'm making here is that once you have at the end of your recursion stack, when you have this transcripts, the verifier doesn't know precisely what operations need to be performed. So that's why you have a VM. So that you can kind of build up the instructions over time, and they can be actually just part of the witness statement. But these VMs are very primitive. It's in like they have an accumulator that you can add stuff into, and you can here's an example instruction set for ECC VM. So the idea is like you can set the accumulator to be the result of multiplication. You can add a multiplication into the accumulator. You can do an assertion that the accumulator equals some value. So basically like super primitive operations. So they're barely virtual machines. Certainly you don't have memory or registers or anything like that. And similarly for the non-native field virtual machine, this is an example that can be expanded, but the idea here is that the idea is to evaluate some somewhat general arithmetic statement that can be used to represent like a large set of non-native field operations. So this may not actually, I think we're probably actually going to change this by the time we have implemented it. But the idea is that you can do things like add and multiply inside the non-native field machine, or you can do like basic linear operations. And similarly, the modulus. The idea is that the actual modulus of this the operation you're performing in the VM is not fixed. So because if that's the case, then you get some other nice stuff for free. It means that you can get big integer arithmetic for free, which is kind of useful for other use cases. It means you can do just arithmetic over arbitrary 256-bit moduli. So you can do sec PG versus K1, as well as stuff over your cycle curve and your main curve. So it's so that is you basically want one row in your non-native field virtual machine to just do some somewhat general arithmetic statement that covers a large amount of operations. So I've done a bit of brainstorming about how to do this ECC VM. Not yet built it because I've been kind of busy with other stuff. But our team is planning on actually doing a spike on this soon. So the idea for the elliptic curve virtual machine is you can just do if you want, like, what algorithm you're going to implement, because you could just do the normal double and add for doing ECC multiplication, but that's kind of slow, it's kind of boring. And with lookup tables, you can do much better. So you can use, basically my thoughts are, take the best algorithm that exists in the real world and just put it in a circuit using lookup tables, where you use this kind of like 4-bit sliding window non-adjacent form method. You basically take your input scalar, your scalar multiplier, and you split it up into 4-bit slices, but each slice isn't 0 to 6 to 15. It's actually minus 15 to 15, where the values are all odd. So minus 15, minus 30, minus 11, etc. That's efficient because it means it's still 4 bits of information, but because negations are basically free for elliptic curves, you only actually need 3 bits of data in your lookup tables, which is nice. So the idea is with this 4-array sliding window method, so the thoughts are that to make such a VM circuit, you will have three distinct blocks in your circuit, like sets of columns. Your first sets of columns will be all transcript validation, where basically you're iterating through the transcript row by row by row, and you're doing all the consistency checks equivalent, like all of the basic logic, everything except the scalar multiplication. So, but you're just making sure that if there's a claimed output, it gets added into the accumulator correctly, that the operation and you're writing stuff to the lookup tables depending on the what the operation is saying. The second block of columns in your circuit is for scalar decompositions and point table computations. So the idea is you're taking each input scalar multiplier and you're decomposing it into this 4-bit non-digested form version, verifying that the decomposition is correct. And then you're writing those decomposed values into a lookup table. So you're saying for a given point index and a given round of your scalar multiplication algorithm, you're shoving the value of your sliding window scalar into a lookup table. Then the next, and so also in this block of columns, you're doing the point table computation. So if your sliding window represents the points p, 3p, 5p up to 11p, up to 15p, then you need to compute these and put them in a lookup table. So that's what the point computation block does. It basically the transcript will basically write a value into the section of your circuit, write a point in, and then you'll double a point to compute 2p, and then you'll compute 3p, 5p, 7p, etc., and you'll put them all in a lookup table that's associated that maps to the various sliding window forms. So those are the first two blocks: transcript validation, and then scalar scalar decomposition, point table computation. And the third block of columns is the actual scalar multiplication algorithm, where basically my thoughts are you have enough columns to perform 4-point additions, and what you're doing is you're basically iterating over your points, pulling out those sliding window values from the lookup from your lookup tables you've computed, then using those to pull out values from your pre-computed point table, again using a lookup protocol, and then you're adding them into an accumulator. And then you're also doing some tracking to make sure that once you've for a given round, once you've iterated through for all of your points, you then need to double the accumulator 4 times, and then you increase the round counter and you go again. So there's a lot of logic to perform, and it's somewhat tricky to encode it all in polynomial arithmetic, but it can be done. I'm fairly confident of that at least. And
so I was going to ask the most efficient algorithms, if you allow variable time algorithms for multi-scalar multiplication outside a circuit, are things like Pepinga and Boscosta that involve sort of putting points into buckets.
Yeah.
I'd always assumed that those were going to be far too complicated to do in a circuit. But that's not what you're talking about. Okay.
Well, I think that Pepinja is actually possible to encode in a circuit. I mean, it's a bit mental. What I'm describing, I think it's sometimes referred to as the Strauss algorithm, which it's not asymptotically optimal, but if you're doing a relatively small multi-scalar multiplication, so like less than 256 points, I believe it's better. It gives you better performance in Pepinja because the constants are better.
Right. Okay.
But yeah, it's but it's just kind of, I guess the devil's in the detail. This is all just paper designs. I'm making some claims here. I'm making a claim that it's possible to implement Strauss in polynomial algebra. I'm making a claim that it's possible to implement Pepinja polynomial algebra if you have lookup tables, but yet to be proven.
I mean, we know it's possible because the arithmetization is complete. It's just, can you do it without making mistakes?
Not the first time around, but my plan is basically implement the algorithm, put it on GitHub, brag on Twitter that it's perfect and it has no flaws, and then I'll get a bunch of reply guys to find all the flaws.
And reply girls.
Sorry. And reply girls. My apologies.
And reply non-binary people.
I want all the angry reply people. Absolutely. So, and by the way, oh yeah, this isn't 49 columns, it's 70 columns, at least. But 70 columns, 8 rows. What really matters is the overall area of your circuit, and that area is very tiny to do a variable-based scalar mul. So, beats the multiple tens of thousands you require for non-native field, non-native scalar multiplications. Yeah, so that's the rough idea for the zk virtual machine. The non-native field virtual machine, I think, is less unknown because I think that the EVM, zkVM folks have done one or two already. But the way I was thinking about doing it is the idea is you have two sets of columns. The first set basically evaluates all of the non-native algebra, like the algebra for a non-native field operation, like as defined by that weird formula in the other earlier slide. And then you have a second set of columns that do the range checks. So the idea is the columns that do the algebra, for each non-native field element that they've got, they shove it in a lookup table to say, oh, wait, do a range check on this. And then you do them in a separate section in your circuit. The reason why you would want to do that is because that way you can get rid of duplicates, so that when you're doing your range checks, you're only range checking unique values and not duplicate values, which will reduce the complexity of the circuit, reduce the amount of work you're doing. So they PLonK or another lookup table protocol to avoid duplicate range checks. So I'm assuming like these column numbers assume that you can do like degree 17 polynomial expressions in your main PLonK polynomial identity, which if you're using ultra PLonK or like a PLonkish style system that doesn't use sum checks is insane because you need crazy FFTs. But I'm hoping that the plan is that the hope is that if you're using sum check protocols, because you don't do FFTs, it actually might be tolerable to have high degree expressions. But if that's not possible, then it just means you need a few more columns. So it's not the end of the world. And then you have the transposition circuit. So this is the bit that's kind of complicated. So the idea is for the elliptic curve virtual machine, the way you want to structure your transcript inputs is going to be in a way that's optimal for the VM, which means you'll want it all on one row. But the way you're writing the instruction into your main transcript is going to be optimal for the width of your main circuit, which means that so here, for example, if the main circuit is 4 columns, and the Grumpkin elliptic curve VM requires 6 columns, then you need to do some funky transformations because what's going to happen as part of this curve transposition subprotocol is that as part of the Grumpkin zkVM proof, these transcript polynomials are going to be opened at a random point. And then what needs to happen is you need to take the information in your main transcript that's over your main curve that maps to these columns and basically interpret it as if they were part of the Grumpkin transcript columns when you're evaluating polynomials. So by that I mean, like in this example, for example, the values here x low and x high need to be they combined form one column in your zkVM. Same with the y low and y high values. And then z1 and z2, they're their own independent columns. Then the opcode is an independent column, but here it's been duplicated because it doesn't need to be duplicated, but there's a redundant value here that's not needed. And so the idea is that the transcripts, this transposition circuit is going to iterate over your main transcript and construct and create instructions for the non-native field virtual machine that are consistent with what needs to happen to compute, to basically open the transcript information as if they were coefficients of the Grumpkin zkVM polynomials. So here, for example, we're saying let's do multiply. So at row I, let's do a multiply and add. Like row I of the non-native field virtual machine, let's do multiply and add, where over like zeta and x mod the Grumpkin prime. So that's basically saying that's evaluating 1 degree of the x polynomial here in the zkVM. And so the idea is that if m is the number of zkops plus 1, then from rows I to m, you will want rows I to m will exclusively be multiply and add over the x coordinates of the information in the zkVM transcript. So basically, what's going to happen is as you're iterating over the main transcript, you're just taking the xi and x low values and you're shoving them into the first into rows I to 0 to m of the non-native field VM, and then similarly, you're then taking actually maybe and then for the next m rows in your circuit, you're evaluating multiply and add on zeta and y. So that gets you the y column, and then you do the same for z1, you do the same for z2, and you do the same for the opcode row. And so there's a weird kind of like there's a bit of a weird transformation that's happening here, because you don't want to open the main transcript polynomials. You don't want to evaluate the main transcript polynomials over the cycle curve modulus. You want to evaluate the polynomials that you would produce, that would get produced by the ECCVM and evaluate those with the cycle curve modulus. So there's a weird funky transformation that has to happen here, but it's very doable. So like the end state of the non-native field transcript after processing the main transcript will be that each virtual machine operation becomes, as I said, like 5 of these non-native field VM operations where you interleave them. So the idea is that the non-native field VM, the accumulator only works on one polynomial at a time. And if this polynomial is degree m, then it means that you're going to have 5 m rows where like the first m, like where each block of m rows is going to be working on one polynomial. So either the polynomial for the x coordinates, the polynomial for the y coordinate, the polynomials for like z1, the polynomials for z2, or the polynomials for the opcode. And yeah, the reason why it's actually m plus 1 rows for each block is because at the final you also need to shove in an assert equal opcode every m rows to check that the resulting computation is lines up with what it needs to be. So this is possibly a slight overcomplication that's to do with the fact that the elliptic curve VM transcript format is not the same as the format as your main transcript format. This problem will go away if you
could you not just make them the same?
You could, yeah, but you could. I can't quite remember why I was so gung-ho on not making the same when I wrote this up. I think the idea here was that actually, yeah, no, I don't know. Perhaps it's just needlessly complex. You just make your main circuits with 5. This kind of goes away. So yeah, yeah. But anyway, if the formats are different, then there's a step you can do to transform them properly. So yeah, details about the transposition circuit. I don't know if it's worth going over this because I imagine this is like a month old and it's already obsolete, and I haven't even written a line of code about it. So, but the idea is, yeah, there's going to be a little bit of algebra if you want to do these transformations. It's a bit of a cost, but it's pretty trivial compared to the costs of actually proving the ECCVM, proving the non-native field VM. So it's kind of not that relevant. Oh, this was an internal talk to my team. So this is an internal development roadmap, but hey, I'll share it with you guys as well. So yeah, this is basically how we're planning on tackling it. Implement the VMs first, and then add this concept of an instruction machine into our like circuit builder code, and then kind of use these VMs that we will build to like in our recursion code, instead of actually brute forcing the elliptic curve operations, the recursive verifier circuit will just instead just use this transposition composer to build up an instruction machine transcript. So yeah, I mean it's fairly complicated, but you know, I think it's eminently doable, and yeah, at a very high level, just the idea of deferring non-native elliptic curve operations that are required to recurse, and then transforming them into a problem over a cycle curve, like reduces the complexity by about an order of magnitude or more compared to brute forcing, and I think has better constants than doing it at each recursive layer like Halo do. So yeah, that's the Goblin PLonK. Lazy recursive proof composition. Thanks folks for following along, and yeah, very happy to answer any questions folks have.
Thank you.
Awesome. Yeah, thanks a lot, Zach. And that was a lot of information in a short time. Thank you for organizing it as well as you did. And if you, like I mentioned, if you want to share this deck with me, I'll put it in the YouTube video. I linked a couple of it. I just for everyone's just to say out loud here. There's some comments, and one of them is Dara referenced the Gemini paper, which I think was about elastic snarks. And Mikhail, one of the co-authors, presented that actually at zkStudyClub. So I'll link that in the YouTube as well. And yeah, and then Dara also linked a zkStudyClub on MSM algorithms, which I'm assuming we discussed as Pippinger. I'm not sure if we discussed what was it with the other one that you mentioned.
Strauss.
Yeah, thank you.
Well, I also mentioned Boscosta. I think I'm not sure which of those were mentioned.
Yeah, but great. Opening up to questions. Does anyone have any questions for Zac or comments on related work? I mean, again, potentially Srinath, maybe. I know we've talked about PLonK a few times in here and Hypernova. So maybe it would be interesting to hear your thoughts on the relevance of this construction to your work. Not to call on you, but if you feel like it would be interesting. So, but yeah, in general, if anyone has questions, feel free and go ahead and ask. Stunned silence follows Zac's presentation. Yeah.
Hopefully some of this might be a bit clearer if we can print it, instantiate it in code.
Yeah, I guess you have a bunch of, I think, costs in there, but I think, yeah, concrete benchmarks, definitely. I think I mentioned this earlier on the side chat that it would be really interesting to see this concretely instantiated and benchmarking that.
Yeah, and of course, after implementing something, it's easier to explain it in general, even if people are not reading the code.
Yeah.
So yeah, keep in hopefully in a month or so we'll have a POC, maybe 2 months, depending on our time, what other stuff gets in the way. But yeah, we're internally we're pretty bullish on this for like taking the pain out of drawing the sting out of the costs for recursion. Yeah, combined with like folding scheme stuff, I think it makes recursion IBC like just utterly trivial, even over arbitrary circuits.
Yeah, I mean, that's obviously a theme across a lot of development in the space. Yeah, it's been interesting to see. I mean, this is something that for Z Prize, we're looking at exploring this year, how to create, some categories around applying different types of recursive techniques to, for computations that otherwise would be impractical. So I'd love feedback on that.
So for the Z Prize thing, would that be sort of define a high level problem and you can use any recursion method to do it, or would it be targeted towards specific methods?
Yeah, I mean, it's a bit of a trade. So the ideal is what you just said, Dara. I think the trade-off in running these competitions is always the more open you make it, the harder it is to judge, basically. You could really, if you wanted to open all the way up, you could say, hey, invent your own new proof system if you want to. But then, of course, I have to make sure that's correct. We have to make sure it's, it has to be audited, right? So, then it's okay, maybe you fix it to like a handful of proof systems or recursion schemes, and so you kind of, there's this tension between like the degrees of freedom you give the competitors and the ease of judging. But the goal this time is to move it up from, last time it was really all about the MSMs low level. And now this time it's more about like, hey, what's a problem we care about? Use any one of this number of schemes to kind of solve this. So we talked specifically yesterday at the steering committee meeting we met, and we talked a lot about Nova and just generally like, hey, how do we work Nova in, and giving people more flexibility. So, hey, you're not just stuck with Nova, but any recursion scheme could work. And just, I think that would be good. Back to the point about concrete benchmarks. And there's so many great new schemes coming out for different, that I think have a wide range of applications. It would be good to just concretely see for this application or this application, like what are we talking about in real world numbers? And so anyway, we're going to be defining the prizes over the next week, and we'll release some more info about that. But yeah, definitely planning on sharing that in the zkStudyClub Telegram group, so it would be awesome to get feedback from you all specifically on your thoughts. But in general, that's the tension. So.
Can I make a very, very tongue-in-cheek suggestion for a prize category?
Absolutely.
What about a roll your own crypto prize? So a prize for building a proving system that does not yet exist in code.
That's interesting. We had not considered that. What we did have one thing that we did consider having is having like a bug bounty of like, hey, all these new crypto systems that people are inventing that, it's not, they haven't been out in the wild yet. In some cases they're already being used. And so it'd be interesting to see like, hey, if anyone can find a vulnerability like that, maybe that's like worth having. But we hadn't thought of the inverse of like roll your own crypto. Yeah,
it's not great for legitimacy and safety, but
it could be fun though. Yeah,
most plausible sounding fake paper. I liked your April Fool's Day thing about that, Zach.
Yeah,
thank you, Dara. Although
at least someone appreciated it.
I mean, I think we should have a prize category for who can come up with the most clever new name for a prefix to PLonK, because we have a lot of different PLonK or PLonK variant names. And so I think, that could be deserving of its own and valuable to any researcher who's writing a new paper about PLonK. So, maybe the IACR would sponsor that one. Cool.
I'm down with that. That sounds like fun.
Awesome. Do we have any more questions for Zach or any just discussion topics that people are interested in or want to comment on generally? Okay, cool. Well, I think I'll cut the video here in a second, but thank you very much, Zach, for being here. Thank you, Dara, for always being a strong contributor to the conversation. And thank you everyone for attending, and we'll see you guys next time. Oh, I guess maybe a quick plug. We have an upcoming, we're presenting some upcoming work or some work that Ariel has co-authored. So we'll be doing that one, I believe, in 2 weeks. Anyway, I'll publish the schedule on the Telegram group, but we have some other really cool sessions coming up. Hope to see you guys at those as well. All right. Thank you very much, Zach.
Cheers. Thanks, everyone. Take care.